The behavior of gases is determined by countless variables. So many variables, in fact, that it's very difficult to accurately predict a gas's behavior. To help combat this difficulty, chemists devised the kinetic molecular theory, a series of approximations and assumptions about the behavior of gases that make them easier to quantify. A gas that abides by the approximations of kinetic molecular theory is said to be an ideal gas. Now realize that in actuality, no gases truly behave ideally. Rather, the ideal gases put forth by kinetic molecular theory offer a framework that we can use to make rough approximations regarding the behavior of real gases. So let's discuss some of these assumptions that we make for ideal gases. First, we assume that the molecules of an ideal gas occupy no volume. That is, if we want to treat the helium in a 1-liter balloon as ideal, we'd neglect the fact that the helium atoms occupy a part of that liter. Instead, we'd assume that there is 1 liter of empty space. In the last section, we mentioned that in actuality, the molecules of a gas occupy only about 1/1000th of their available space. So it's not such a stretch to simplify even further and assume that the molecules occupy no volume at all. Now, ordinarily, we know that molecules can exert all types of forces upon one another, whether they are attractive or repulsive. But in an ideal gas, we assume that the molecules are widely enough dispersed that these attractions and repulsions are negligible. In fact, we go so far as to assume that the only forces conveyed by gases are due to molecular collisions. And regarding those collisions, we assume that they are completely elastic. That is, both the energy and momentum of the colliding molecules are conserved. But more on that in physics. Lastly, we assume that increasing temperature causes a direct increase in the molecule's kinetic energy. Collectively, all of these assumptions allow us to use the ideal gas law, PV equals nRT. P is the pressure of the gas in atmospheres. V is the volume in liters that the gas occupies. N is the number of moles of gas. R is the universal gas constant, whose value is 0.0821. And T is temperature in Kelvin. Using different units, the universal gas constant is sometimes reported as 8.314. Though both are valid, if we use units of atmospheres, liters, moles, and Kelvin, we will always be able to use this value for the gas constant. Also, don't get confused. We said that in an ideal gas, the volume of the individual molecules is negligible. But that doesn't mean that this volume term is 0. This volume represents the volume of space that the gas is free to occupy. The volume of the jar, not the volume of the molecules themselves. The ideal gas law gives us an idea of the relationships between pressure, volume, and temperature. The volume of this jar is constant. So is the number of moles of gas inside the jar. And of course, the gas constant is also constant. So we can see mathematically that increasing the temperature of the gas will necessarily increase its pressure. This makes sense intuitively. If we increase the gas's temperature, the gas molecules have more kinetic energy. Their collisions become much more forceful, and so they exert a greater pressure on the walls of the jar. Now let's substitute the jar's lid for a plunger that can move up and down freely. Volume is no longer constant, since the jar's volume can change. But let's hold temperature constant. If we depress the plunger, we compress the gas, and therefore lower its volume. With the gaseous molecules forced into closer proximity, this corresponds to an increase in the gas's pressure. This is precisely what's predicted by the equation. With all of this being held constant, a decrease in volume must induce an increase in pressure, and vice versa. Lastly, let's look at a scenario in which pressure is held constant. If this gas is heated, its molecules will carry greater kinetic energy, and previously we saw that that corresponded to pressure buildup. But now we said that pressure is being held constant. To keep the pressure constant, the gaseous volume must increase. The added space will help diffuse the bolstered energy of these gaseous molecules, thereby allowing the pressure to remain constant. So, as predicted by the ideal gas law, temperature and volume are directly related. And of course, if we did open the jar and add more moles of gas, N would increase, and as a result of the crowding of molecules, pressure and/or volume would increase proportionally. Interestingly, the ideal gas law doesn't at all depend upon the identity of the gas. All ideal gases behave identically. That being the case, all ideal gases have the same volume, which at STP is 22.4 liters for each mole of gas. Suppose you are asked, ideally, what will happen to the volume of 1 mole of neon at STP if you double its pressure at constant temperature? We know the standard molar volume is 22.4 liters, and according to the ideal gas law, we know that pressure is inversely related to volume. So doubling the pressure will halve the volume, which leaves us with 11.2 liters.